So because it will be a little bit more involved mathematically compared to the previous two lectures, I would request your patience. And of course, I would also request your concentration, okay, throughout these lectures. These will basically work as the baseline for the remainder part of the topics that we will be covering, inshallah, in this course. Okay. So let's start and let's get into the electrical part or electrical modeling part of the synchronous machine. We will still call it as the dynamic modeling because the part that we covered earlier in the last two lectures, we will see that ultimately those two or that second order system will be still included in whatever modeling we are going to achieve in this slide finally. Okay, so that's why it is still a dynamic modeling of the synchronous machine, but however a little bit more elaborate. In an elaborated manner, we will look into the dynamic modeling. So what we'll be doing, basically we'll be taking the example of a salient pole machine. So as you know that the salient pole machine, we can clearly identify or you can clearly distinguish the number of poles present in the system. So let's look at the outline of the top of this slide. So first of all, we will be looking into the schematic of a three-phase machine, that is a synchronous machine. And as I told you, just told you that it will be an example of salient pole machine. Then we'll be looking at some standards which are basically followed in the classification of dynamic model. Any three-phase machine, you can classify them, and just by looking at the number that is put against the classification, you can easily identify what is actually inside the machine, okay? Which part is taken and which part is not while trying to model the system dynamics. So that will be taken in the second item. The third item will be looking into the voltage expressions or voltage equations for the synchronous machine, as well as the flux linkage equations, the permeance of the machine, and as well as the inductance of the machine. And we will also look at the new concept, probably for some of us at least, if not all of us. The Parkes transformation will be introduced, and some of its application will be discussed for very simple expressions or very simple systems, and then we'll be using that Parkes transformation for simplifying some of our expressions that we will achieve up to a certain point through our development of the synchronous machine modeling. Then of course, as we did for the second order model or for the classical system, we will also look out for the per unitized model. Okay, so the per unitized model will be developed. And finally, out of all these discussions, we'll be going slowly again, actually going through some assumptions, we should say simplifying assumptions. And finally, we will see that we can represent the electrical part of the synchronous machine. The least that we need to represent the electrical dynamics of the synchronous machine is only a single ODE would be sufficient. However, you can also go for more than one. Okay, so if I add up that single order ODE or first order ODE that we will reach at after the conclusion of this slide, we will add that single dynamic equation with our previously developed second order model. So ultimately we will have a third order model. So one of the ODE will represent the electrical dynamics of the synchronous machine, whereas the remaining two will represent the acceleration of the rotating part of the machine. However, as I said, you can go for much more complexity here. However, for this course, we will be resorting to the third order model, okay, at the end. But we have to go through some difficult steps actually to reach at this stage, okay? So let's start our journey slowly with the schematic of the synchronous machine. Can you see this picture clearly, or should I zoom in a little bit more? Is it okay?
Yes, sir, it is okay.
Okay. Let's make it 100 exactly. Okay. So probably already you have seen this, so I'm not going to discuss too much about this. So just for a recap, quick recap, we have a salient pole machine. So These are nothing but our stator windings. So these two comprises the phase A of stator coil. These two comprises the phase B of stator coil, and these two comprises the phase C of stator coil respectively. And these two here across the rotor coil, these are the cross section, remember, cross sectional view of the coils. These are the rotor coils or the main field winding or the main winding, whatever you say. So this winding basically carries a DC field. So you can have a permanent magnet. If it is a permanent magnet, then of course you don't need these rotor coils. However, we are considering that we don't have permanent magnet. Rather, we are assuming it to be an electromagnet. So we have to magnetize the core by the help of some external field, DC field. Okay, so these are our rotor coils. So you have 3 sets of coils in the stator circuit and 1 set of coil in the rotor circuit. This is the most simplified representation of a synchronous machine, salient pole synchronous machine, that we have already discussed in our previous lecture. Okay, so there is nothing new in this slide. Just to have another little bit of quick recap with this, theta m. What was theta m? This was the angle of the rotor axis, rotor center axis, or the D axis, direct axis. That was the representation of the rotor position actually. So this is the representation of the rotor position, and that rotor position is measured with respect to the A-axis MMF. This is the MMF for the A-axis current. Okay, whatever current is flowing through this AA prime, then due to that current flow, whatever magnetic flux is being established, the direction of that magnetic flux is represented by this capital A-axis. Similarly, whatever current is flowing through this BB dash, that MMF, that resulting MMF is represented by the direction of that resulting MMF is represented by the capital B axis, and similarly for the C axis is represented here. Now there is a little difference between these ABC axis, MMF, and their positioning, and the difference is actually with respect to the rotor coils. Okay, rotor coil positioning and their MMF. Now let me ask you one thing. Okay, try to answer it carefully. As you are looking at coils A, B, and C, can anyone tell whether these 3 sets of coils are stationary or moving?
Stationary.
These 3 coils are stationary. Excellent. So we can say that stator coils are stationary. So stationary, both are remaining same. So stator coils. So the stator coils are actually stationary, or we better write fixed. Fixed in space or fixed in position, right? Fixed in space. They are not moving at all. So they are fixed in space until and unless you are moving the whole body itself of the machine. So until and unless you do that, actually it remains fixed in space. Done. But what sort of field or what sort of current are actually they are carrying? Is it DC or AC? Is it changing with time or fixed with time?
Changing with time.
Changing with time. Excellent. So the stator coils, although the stator coils are fixed in space, but the field, the stator field, the field that they are carrying or that they are producing actually, that those fields are actually AC. Okay, so that means they are function of time. They are some function of time. Is that clear? So the stator field are actually the function of time because they are AC, they are alternating in nature. This is about the stator coil position and the resulting field due to the current flowing in the stator coils. Clear? If you have any confusion, please ask me. Okay, no problem. Next, come to the rotor coils. What about the rotor coils? Are they stationary?
No, sir. Rotor is moving.
Rotor is moving, so the rotor coils are moving. So the rotor coils are moving. Excellent. So the rotor coils are not fixed in space. Okay, this is the conclusion. The rotor coils, because the rotor has to be moved with the help of the prime mover at a certain speed. So the rotor coils in space, they are moving. What about their field?
DC.
Their field is DC. So their field DC is actually constant. So the field DC, their field is not a function of time. Is it okay? So there is a clear difference between the positioning of the rotor coils, the stator coils and the rotor coils. The rotor coils are moving with respect to time. They are moving actually in space. So with respect to space positioning, they are not fixed. With respect to space positioning, the rotor coils are not fixed. The stator coils, with respect to space or position, they are fixed. On the other hand, the stator fields, with respect to time, they are changing. But in the rotor coils, because we are supplying DC, so the field itself with respect to time is unchanged. Okay, the magnitude of the field is not a function of time. Okay, please keep this in your mind. And there are some other nomenclatures or discussions that is being mentioned here. It is known to you. The direct axis, D axis, it's the name of the direct axis in short. Or we may also call it the polar axis, because it goes through, actually, it cuts through the poles. Okay, it cuts the poles into equal to halves. Okay, North Pole, it cuts it into halves, and South Pole, it also cuts it into two halves. So that's why it is the polar axis, or in short, it is D axis. The quadrature axis, it is actually 90 degree in phase with the D axis, so it's the name is quadrature. Or you can also, in some places, you may also find it to be named as interpolar axis. Means it is the pole, it is the axis that is assumed to be in between the poles. Okay, interpolar, in between the poles, at the midpoint of the two poles. Or in short, we will call it Q axis. So mostly in our lectures, we will be following these D axis and Q axis. Dot means the current is coming out of the page. So these dots mean the current is coming out of the page, the arrowhead. And the cross means the current is going into the page. This is the tail of the arrow, tail end of the arrow. FD, this is the main field winding. And oops. Let me start the recording. Okay. So FD, so we were here basically. FD, this is the main field winding, and theta M is, as I said earlier, is the angle is created between the D axis, the polar axis, and the MMF axis for the coil in the A, currents in the coil A, stator coil A. So now we move into a little bit more complex thing slowly. So let's see. So now we introduce damper windings in our machine model. So as you can see clearly that these are the cross-sectional view again. So in the D axis, so let's start with the D axis. So in the D axis, initially we had only FD and FD dash. So that is still there, okay? Because this is the field winding. Without the field winding, actually, unless if your machine is permanent magnet type, you are not going to excite the coils. You are not going to get the main field. So as we said earlier, that we are considering it to be an electromagnet. So FD and FD dash will be there always, okay? Whether it is a even in the most simplified case, FD and FD dash will remain there. Now we are introducing the damper windings in the D axis. So you can see 1D and 1D dash. And in the Q axis, in the Q axis, we are representing two damper windings. One is 1Q, 1Q dash, and another one is 2Q, 2Q dash. Okay. And this is only one of the possibility. This is the representation of only one of the possibilities. What are the other possibilities? We will see it within maybe 2 or 3 slides. We'll be looking into the other possibilities. Okay, this is only one of the possibilities where the damper windings are actually represented here. So now can you tell us, anyone, if you look closely, the D-axis coils, are actually placed here, okay? Maybe anywhere along this line they can be placed. And the Q-axis coils are actually placed in this manner, okay? Q-axis coils are placed in this manner. So what will be the directions of the resulting fluxes for these currents in these coils? Like, let's say if I say some current is flowing in the D-axis coils out of this 1D and going into 1D dash, what will be the direction of that MMF?
D-axis.
So what I'm saying is this, okay? Let's say some current is moving out of this and going into this. So
right hand.
Yeah, right hand rule, thumb rule. So
thumb rule.
you get it, okay, along this D-axis, okay. What about the Q-axis? So similarly, this, so if I just erase this one, so this 1Q, this current is coming out and going into this. So you can see that clearly it will be along the Q-axis, right?
Yes.
Similarly, the 2Q1, if you again follow the direction of the current, it will be along this direction. So this is why actually they are placed in such manner, okay? So that whatever MMF is being obtained from these coils, they actually follow whatever axis we have drawn here, okay? That's why they are being actually placed on the schematic diagram in this manner, just to follow our directions. So now we also introduce now we actually get rid of the cross-sectional view for those additional damper coils. Okay, instead of that, what we do, we introduce some physical representation of the coils. So you can see along the A axis, we have some representation of coils. Similarly, along the B axis and C axis, we are representing some coils. And also we are representing 2 separate coils along the D axis, one for the field coil and one for the 1D coil. And we are also adding 2 coils along the Q axis, one for the 1Q coil and one for the 2Q coil. Okay, so these are the addition of the coils. Now let's look into the direction of currents through these coils. Okay, so before you start modeling of your machine, you have to go through some convention. Okay, the convention is basically regarding the flow of current into the coils. Okay, flow of current into the coils. So in this lecture, whatever lecture that we are going to discuss, we are going to assume that if it is a generator, what do you expect out of these coils? Coil A, coil B, and coil C. Do you expect electricity output or input?
Generator from output.
Generator will provide output. So we will assume that if, let's say, if you have any coil, and you are saying the coil is providing output, we will assume it to be negative direction of current flow. Is it clear? And if there are any coils where we are putting the current direction into the coils, we will assume it to be a positive directional current. So this is the convention that we are going to follow. However, in some books, they may alter this notation, but then they have to follow that strictly throughout their derivation. Okay. So is it clear? If any current is coming out of the coil, we are going to assume it to be negative direction. If any current is going into the coil, we are going to assume it to be positive directional current. So keeping these two things in mind, let's say what they are doing. So because the A axis, the B axis, and the C axis, these three are the stator coils, and from the stator coils, actually, we expect the current to be coming out into the load, okay, to the load, out of the machine. So you can see this is coming out, this is coming out, and this is also coming out. Okay. Next, what about the field coil? Do you supply current or do you take current out of it? Field coil, FD.
Supplying current.
We supply current. So you can see clearly we are supplying current. Okay. IFD. Maybe it is too small, but that's why I'm encircling it, highlighting it. So IFD, this is the field coil voltage, and this is the corresponding field current. This is the stator current output, and this is the corresponding output voltage across the winding or across the coil. Similarly, this VB, it is the voltage across the coil, induced across the coil. VC is the voltage induced across the coil. VFD, this is the voltage supplied to the coil, and IFD is the resulting current flowing into the coil. What about 1Q, 2Q, and 1D? Remember, these are damper coils. Okay, these are damper coils. These are not conventional type coils. So what do we actually do with the damper coils? Can anyone remember physically what is done with the damper coil terminals? Anyone?
So they are shorted, sir.
Damper coils are short circuited. So that's why you can see that V1Q, V2Q, and V1D, these are actually 0. This will be, although they are being shown here, V1Q is being shown, V2Q is being shown, and V1D is being shown, but practically they will remain 0. Okay, because in practice they are actually short circuited, and due to that, actually, whenever there are any voltage induced in the damper coils, that will be actually fed into the coils. Okay, that will be fed into the coils. That means whenever this V1Q, V2Q, and V1D, this will become non-zero, then the resulting current will be actually fed into the coils, and there will be some damping torques. So that's why you see the current direction is going into the coils, and these currents will only become non-zero whenever these voltages will be non-zero. That is quite clear. Now, when will the damper winding become active?
Transient period.
During transient period. As we said earlier, during transient period only, the damper windings will carry some current, because only then, due to the induction machine action, there will be some induced voltage here. Otherwise not. Otherwise they will sit there idly, or they will be like a dead winding. That's why they are also known as amortisier winding. Okay, another term used for damper winding is amortisier windings. Okay, so is the current directions clear for all the coils? The current directions and voltages, the magnitude of the voltages, etc.
Yes, sir.
Okay, so let's move on. Let's move on. Okay, now come to the classification. As I said, that this configuration here, that only one D axis winding additional and two Q axis winding, this is only one of the classification which are actually shown in this table. Okay, so if you look into the table, along this line you have number of windings in Q axis. Okay, so along the columns, the number of windings in Q axis will change, whereas along the rows, the number of windings in D axis will actually change. And by combining these two numbers and putting a dot in between them, we are simply getting different models for a synchronous machine which are available in the literature. So first model, okay, the first term here, the first number is representation of the number of coils in the d-axis. And the second term is the representation of number of coils in the q-axis for all of these numbers present here, all of these models present here, okay? So let's start with this one. So what is meant by model 1.0? Can anyone tell? It means, well, it means that we have one coil in the d-axis or one set of winding in the d-axis and no set of winding in the q-axis. What does that mean? Does it mean this one? Remember, we are talking about q-axis coil and d-axis coil, okay? So in this figure, how many coils are there along the d-axis? How many set of windings along the d-axis?
So both axes have zero coils. D-axis, no, this is not shown. There is no any coil in D-axis from the figure. I can see.
Not agreed totally. Anyone?
So there is field coil.
There is
along
field coil. There is a set of coil. You can't ignore this, right? You can't ignore this. There is a coil. There is a set of coil. As I said, even for the most simplified representation, you can't ignore the presence of FD and FD dash, unless it is for permanent magnet machines. But all these classifications are made for electromagnet. So actually you can't operate your synchronous machine without the field coil. So at least one set of coil should be present along the d-axis, right?
All right, sir.
And no sets of coils, be it field coil or any other damper coil or any other set of coil, no set of coil is present in the q-axis. So this is 1.0 actually. Clear? What is 1.0?
Yes, sir.
And this is q-axis. Done. So now it should be pretty clear. The next ones should be pretty clear. Okay, so the next few ones should be pretty clear. What is 1.1? How will it look like? 1.1. Can anyone tell? 1.1 means one set of coil in the d-axis, and how many sets of coil in the q-axis?
One set.
One set of coil. So let's put one set of coil along this. And let's put a dot here, and let's put a cross here, and let's say this is 1q and this is 1q dash. Okay, so this is one set of coil in the d-axis, and this is one set of damper coil. It's a coil, of course, it's a set of coil, but it is a damper coil. So this will be your 1.1. Okay, understood?
Yes, sir.
Okay, what is 2.1? Model 2.1.
D-axis should
Just simply add another 1D and 1D dash. Okay, I'm not putting the dots and cross, probably it will kill some time. Okay, 1D and 1D dash, and here you put 1Q and 1Q dash. Okay, so two sets of coil in the d-axis and one set of coil in the q-axis. Done? Very easy. What should be 2.2?
two set in D-axis and two set in X-axis.
So I'm not going to draw it again because it is already with us. So this is 2.2, right? Two sets of coil in the d-axis, one is FD and one is 1D, and two sets of coil in the q-axis, one is 1Q and another one is 2Q. Okay, this is 2.2. And similarly, you may have other combinations, but that would be limited to these combinations only. Okay, there are some combinations which are not accepted. Okay, for example, model 2.0, that's not acceptable. What would it look like? 2.0? 2.0 means you actually only have added one set of damper coil in the d-axis, but none in the q-axis. So that is actually not acceptable. As soon as you are adding one set of coil in the d-axis, you have to add another set of coil in the q-axis. Okay, so there are some combinations which are not acceptable, And the final one, the most complex one, which can capture the most, probably the most complex phenomena that, or most complex dynamics that comes through the synchronous machine study, that is 3.3. So 3.3 means what? 3.3 means probably you have to add 2D dash here and 3Q dash here. Okay, that would be 3.3. But our study in this course will limit in with this model. Okay, in this lecture, in this slide, actually we will be focusing on this 2.2. Okay, model 2.2. We'll be deriving the model for 2.2 at the very beginning, and then slowly we will going for some simplifications just to make life easy. Now let's look at the stator winding voltage, simple KVL. So if you look at the windings now, look at the windings carefully. Let me zoom it in for you, just for your convenience. So if I am looking for the equation of voltage here, what would be the voltage? Consider that this coil, within the coil, you have, of course, you can't expect to have a purely inductive coil. There are some internal resistance, internal losses, right? You can't ignore that. So let's say this is your resistance of the coil. This is your inductance of the coil. Resistance, of course, is not shown here just to save some space. But if you want to have some generalized representation, then you should include this R. So let's say this is your RA, resistance of the coil A, and this is your LA or something like LA. And because it is a stator coil, so, and because it is generators, we expect some current to be coming out of it, that is IA. And the induced voltage that you will get out of this coil is VA. Now, what should be the KVL here? VA, what should be VA equals to?
I into RA plus LA.
IA into RA, then
RA plus LA.
RA plus LA, it's not possible, man. Either you have to make LA into X and add some J operator with that.
Yes, sir. I need to J operator. Yes.
Okay, so that will give you again some steady state representation. But because we are looking into the dynamic model, so you have to go for this representation. Okay. This d lambda over dt. What is lambda? Lambda is the flux linkage. Okay. What is flux linkage? You can say it is some sort of n phi. Remember? N is the number of turns in the coil, phi is the flux cut by the coil, and lambda A is the resulting flux linkage. So this is n phi. This is induced voltage expression, induced voltage expression. So is it okay? Now, what is the problem here? Let us see. Is VA the output from the coil or input into the coil?
Output from the coil.
VA is the output of the coil, but from here it seems that, and okay, and what is this? This is the induced voltage actually. Okay, this is the terminal voltage actually available here, and whatever voltage is induced, that is d lambda A over dt, that is due to this flux linkage. So what should we do here? We can change the sign here simply just to make these things valid. Remember, current coming out of the stator coil is taken as negative, right? We agreed with that. This is the assumption or convention we are going to follow. So because this is current coming out of the coil, so we will place a minus sign here. Now it is solved. This is the output voltage, VA, and this should be higher than this. So you can also write d lambda A over dt equals to VA plus IARA. Is it okay? Because VA is the output volt, output variable for this circuit. It's not the input variable for this circuit. VA is the output variable. So VA should be somewhat less than whatever voltage is induced in this, okay, in this coil. Understood the direction of IA, why we are putting minus? You can explain it into two different ways. One way is to simply say, well, current is coming out of the circuit, so there should be a minus sign before IA. It is not going into the circuit, okay? If this is IA, then it is fine. There should not be any minus. But because current is coming out of the circuit and VA is the output terminal voltage for this circuit, for this coil, so VA should be less than whatever voltage is actually induced in this coil. So that's why this is another way to explain this minus sign. So similar sort of expression can be written for other two sets of stator coils, right? If this is understood, then we can move forward. Very easily we can say, well, these are the three equations then, okay? VA is minus RS IA, YS, because we have considered that, well, for phase A, phase B, and phase C, all of them, they belong to the stator circuit, and we here assume that, yeah.
Sir, if current enters to the coil, then this sign will be plus RSIA, and sir, what will be the sign of this del?
We will show it. We will show it whenever this comes. Probably in 1 or 2 slides that will come. Okay, we will show it. Okay, so this this RS is basically, as I was saying, this RS, we have assumed that this is equal to RA equal to RB equals to RC. Why? Because we are considering that this is a balanced set of winding. They have balanced inductance, balanced value of inductance, and balanced value of resistance for each coil. Okay, they are same. RS is equal to RA, phase A resistance, phase B resistance, phase C resistance of those coils. So that's why we are writing it RS. S here simply stands for stator. Okay, that's why. So RS is nothing special. It is same as RA, RB, and RC. I've just this is a shorthand notation for each of the coils. And then d lambda A by dt, d lambda B by dt, plus d lambda C by dt. What about, these are stator winding voltage. What about the rotor winding voltages? This is the answer to your question, okay? VFD. What will happen to VFD? Remember, is current going into VFD, the field coil, or coming out of the field coil?
So
Let's
it's
see.
It's
going into the field coil. You see IFD here. IFD going into the coil. So the polarity of IFD should be plus. And VFD is the source voltage. Remember, VFD is the source voltage for the circuit here. This is the external field voltage. Remember? So this is the feeding, voltage feeding. So this voltage should be higher than whatever drop is happening, whatever voltage is being induced, and whatever drop is there across the resistive part of the coil. Okay, so that's why simply it can be written as this: RFD IFD plus whatever flux linkage is there across the inductor. Okay, V1D, it is the D axis, and we said that V1D, V1Q, and V2Q will only become non-zero when there is any transient or dynamic situation. Otherwise, V1D, V1Q, and V2Q all will be zero. However, their current directions, as we assume them to be positive, going into the circuit or going into the set of coils. So you don't see any minus sign here. All of them are positives. Okay. But let's say if you are trying to model the motor, synchronous motor, where will be the change? Simply here will be the change. Okay, because in a synchronous motor, only thing that changes is your flow of energy. Okay, from synchronous generator, if you compare it with the synchronous generator, it provides the electrical output. That's why the current is coming out of the coils, so that's why it's negative. But for synchronous motors, you will see that this will become positive, and this VA, VB, and VC, this will become then input voltages into the 3 stator coils. So simply just you make them positive and you proceed on with the derivation as we are going through here. So the modeling part is almost identical. Simply you have to take care of the current direction in the stator coils for synchronous motor. Okay. So now again come back to synchronous generator, which we were discussing earlier. So any question about this? For simply because the current is being fed into the field coil and the current will work as input to the system for 1D, 1Q and 2Q once there are some non-zero voltages. So that's why these are all plus, and these terms are actually associated with the flux linkage in these in those 3 circuits. Now actually we want to express this lambda A, lambda B and lambda C. We want to go into the detail of this slowly, and that will be a little hectic job, but be patient, then inshallah it will be clearer as we move on. So we want to look into this, we want to look into this, we want to look into this. Similarly, we want to look into this, this, this and this. Okay, and of course the associated d by dt will be there. So now let's see how we can calculate these flux linkages at first, and then we will be coming back to these expressions and we'll be plugging those flux linkage expressions into these expressions, and we'll be calculating the derivatives and we'll be finding out the voltages slowly. Okay, so this is in which direction actually we'll be moving in our next few lectures. Okay, so what is lambda A? How many coils are there in total? So there are actually 3 sets of coils in the stator circuit, A, B and C, and in the rotor body there are 4 sets of coils. One is the field coil and another 3 sets of damper coils. So in total we have 7 sets of coils. Okay, now all of you should know this, but I'm just giving you a small recap because these are magnetic circuits. So if there is any current flow in any of these coils, there will be some flux linkage of whatever flux will be generated due to this IA. Whatever flux will be generated, there will be some of the flux will be linked with this coil, and at the same time that those flux will be also those flux, there is every chance that those flux will be also linked with all the other coils present in the system, isn't it? So some flux will be self flux linkage and some flux will be mutually flux linkage. Is it okay? Self flux linkage and mutual flux linkage. So we will be looking into that slowly. So let's say we want to express now only lambda A, and these are nothing but matrix and vector multiplication. So lambda A, lambda B, lambda C, these are stator winding flux linkage vector. You can also write it as this lambda A, B, C. Means there are 3 components. One is lambda A, another one is lambda B, another one is lambda C. This is the shorthand notation. This is the elaborated notation, vectorized notation. So let's start with lambda A. Now we have the equation of lambda A. Okay, lambda A is dependent upon IA. That means whenever there is any current flow in coil A, there will be some flux linkage lambda A, right? Due to what? Due to its self-inductance of the coil. And the self-inductance of the coil is represented by LAA. Similarly, when there is any any current flowing in the coil B, there will be some flux linkage with coil A due to these mutual inductance LAB. Similarly, whenever there is any current flowing in the stator coil C, there will be some flux linkage lambda A, which will be created due to LAC. Clear? Now, why there is minus sign? There is minus sign because IA, IB, and IC, these are actually coming out of the circuits. So that's why this minus sign will take care of that. Okay. So this is the flux linkage portion of the flux linkage, or part of the flux linkage that comes or that generates, that originates due to the stator current flow in IA, IB, and IC, and due to these three inductances: self-inductance, mutual inductance between phase A and B, mutual inductance between phase A and C. But remember, we have 7 sets of coils. These 3 takes care of only 3 sets of coils. We also have another 4 sets of coils. So we have to take care of that. So how to do that? Simply, there are some current flows in the field coils. So there will be some part of lambda A which will be originated due to the current flow in field coil and the corresponding mutual inductance between phase A and field winding. This is stator to rotor. This is stator to rotor mutual inductance. Okay. LAA, this is purely self-inductance, stator self-inductance. What is LAB?
Mutual inductance.
Between whom?
Between A and B coil.
Yeah, this is stator to stator mutual. Okay. This is stator to stator mutual. There is nothing to do with the rotor, but this is stator to rotor mutual. So both of them are mutual, but their locations, their positions are different. Okay. So LAB and LAC both belong to this family. LAA is a stator self-inductance. LAFD, this is the mutual inductance between stator coil A and the field coil. Similarly, LA1D and I1D will provide some part of lambda A. LA1Q and I1Q will provide some part of lambda A, and so on. You get it? So there will be 7 entries due to these 7 current flows and due to these 7 different types of inductances. Okay. Some of them are purely self-stator, self-inductance. Some of them are mutual, but between different stator coils. Some of them are also mutual, but between stator and rotor. Okay. So there is a difference. There is a difference. Again, I'm highlighting this. There is a difference between the current direction in these 3 coils, IA, IB, and IC, and these 4 coils. Okay. These 4 coils, they carry current into the circuit. So that's why they are positive. The direction is positive. But these 3, they carry current out of the circuit. So that's why they are negative. Okay. So that's done for this slide. So in shorthand notation, what we can do, we can simply represent them by this last line of this slide, that is lambda ABC bar is the vector for this, representing this lambda A, lambda B, lambda C. This whole thing, LAA, LAB, so LAA, LAB, and LAC, LBA, LBB, LBC, and so on. These 3 by 3 matrix, this is purely linked up with the stator. Okay. All are stator to stator quantities. So we call them LSS, stator to stator. This is IABC, the shorthand notation for the 3-phase current flowing in the stator. What is this? This is stator to rotor mutual inductance matrix. Okay. So it has 3 rows, and so it is 3 by 4. So it is LSR, stator to rotor. S for stator, R for rotor, and we have 4 rotor currents in the 4 rotor coils. What about rotor winding flux linkage? Similarly, you can analyze the rotor winding flux linkage. So there will be 4 of them: lambda FD in the field winding, lambda 1D in the D axis damper winding, lambda 1Q and 2Q in the 2 of the Q axis damper windings. Again, you see the minus sign because IA, IB, IC, these are coming out of the circuit. So that's why minus sign. This first element, what is this? Is it a mutual or self?
Mutual, sir.
It is a
Mutual.
mutual. Between whom?
Field and
Field and
Between
A.
field and A axis. Excellent. So I think you have understood. So I will proceed quickly from here. Similarly, this is 1dA. So 1D belongs to the damper winding in the D axis, and A belong to the stator coil. A axis is stator coil. What is, okay, so all these blocks now belong to LRS in short, means it is the mutual inductance between the rotor circuit and the stator circuit. Okay, mutual inductance between the rotor circuit, because the rotor terms are coming first, appearing first. So FD belongs to the rotor circuit. So it is LR, then S. The second term, the last term here coming, that is the stator coil. So that is LRS, mutual inductance between rotor and stator coils. And IABC comes from here. Then what is this? LRR. The name itself says it is the
rotor to rotor.
rotor to rotor relationships. So LFD, LFD, FD means it is the inductance, self inductance. Actually, FD means self. Okay, it is the self inductance for this field coil. 1D it is the self inductance for
Damper coil.
damper coil in D axis. Similarly, 1Q and 2Q. And these are the mutual FD 1D. This is mutual between whom? Between the two coils present in the D axis. Okay, this is mutual between whom? The two coils in the Q axis. And this is also the mutual, the two coils between the Q axis, in the present in the Q axis. Now, interestingly, we have some zero entries here. Can you explain why? And what are these actually? How can you write this? If you want to write this entry, something like this, what would you write? You would write something like this, LFD 1Q, right? And this one would have been LFD 2Q. Now they are entered as zeros. Can anyone explain why?
Sir, are they shorted?
No.
Sir, D axis and Q axis fluxes will, I guess, they won't be mutually inductive. Is it something like
Because, can you repeat, please?
that?
There was
Sir,
some
I
noise.
said, okay, sir. Sir, I think because D axis flux and Q axis flux will not be mutually inductive due to
Yeah,
the difference
because of
between-
their presence of these
Yes, sir.
90-degree orthogonal. They are orthogonal, okay?
Yes.
So they don't have any mutual coupling. Excellent. So they don't have any mutual coupling. So they will be zeros. Okay. So you can see clearly wherever you have any coupling between D and Q axis, they are providing zero entries. Excellent. Okay, understood. Because of this 90-degree, any coils present here and any coils present here, there will be no mutual inductance and there will be no mutual coupling. That is to say, there will be no flux linkage finally. Okay. So whatever current is flowing here in this coil, and there will be no flux linkage with this coil due to the current flow in this coil. This is what is meant by these zeros actually. Excellent. Okay, so LRR, this is in short the matrix which represents the inductances present in the rotor circuits. Okay, we probably I missed 5 minutes. So if you allow me a few minutes, I can go through a small topic. May I proceed?
Sure, sir.
Okay,
Yes, sir.
thank you. Okay, maybe little few more minutes. Let me finish this one and then I will stop, probably 10 minutes. So let me see how far I can go. Well, now we will look into a small concept of the stator flux permeance. We will represent that by a letter capital P, and that permeance is observed with respect to the rotor position. And remember, rotor position, we call it as theta m. Okay. Now, to understand this thing, stator flux permeance, the nature of the stator flux permeance, or the variation of stator flux permeance as a function of theta m, let's look at these two figures closely. What was theta m? Theta m, remember, theta m was the angle created between the d-axis and the a-axis, right? So this was the theta m originally. Remember?
Yes, sir.
Okay. So let's say at time t equals to 0, at any time t equals to 0, this rotor coil or this rotor is aligned in such a way, the rotor is positioned in such a way that the d-axis coincides with the capital A axis. Okay. So what would be theta m?
0 degree.
Theta m would be 0, very clear. Now let's say after some time, of course, the rotor will be moving, right? The rotor will be moving with the help of the prime mover. But remember, A axis, B axis, and C axis, in all these figures, they are along the same direction. So we are not touching them. We're not changing their direction because we can't. We are only changing the positioning of D axis and Q axis because actually the rotor is moving, supposed to move with respect to time. So at this position, let's say theta m is 90 degree. Okay. Now, let's come to the permeance. What is permeance? In short, quickly, we don't have much time. What is permeance? How is it related to reluctance?
Sir, it's opposite to reluctance.
It's
So
inverse.
basically, sir, permeance is, sir, the extent magnetic flux is linked with a coil, I guess, something like that.
Yeah, it actually expresses the ability
Yes,
of
sir,
a magnetic
fun-
flux.
magnetic
to be-
flux.
yeah, how much the medium, it is actually the property of a medium. Okay, how much the medium is allowing me to establish the magnetic field. Okay, so that is permeance. So it is the allowability, whereas the reluctance is the opposite of permeance. How much the medium actually resists me to establish the magnetic field. That's why they are inverse. Similar to resistance here, okay? How much it resists the electron flow. For electric circuit, for magnetic circuit, it is reluctance. And permeance is the same as you can say the conductance. Okay? Resistance 1/G, you can say for impedance, some sort of that. So now let's come back to permeance. We are looking at the permeance, stator flux permeance. That means how much, or what is the allowability, how much the medium is allowing me to establish flux, or how easily I can establish flux through a medium or through a path under consideration. So now let's see, we are starting at theta m equals to 0. So now let's see, we are trying to find out how easily we can establish MMF along the A-axis. Okay, how easily we can establish MMF along the A-axis. Now, what is this material? Can anyone tell? Probably I asked the same thing earlier in one of the lectures. What is this? What sort of material is this? Remember, this is the cross-sectional view of the rotor body. This is the rotor core. Now tell me, what's the body, what's the material? Is it air?
Iron core.
It is iron core. Excellent. It is iron core. What about this? This is the stator coil, stator core.
Copper.
Copper is actually the coil itself. Sorry, it's not the, these are the coils. They are placed into the slots actually. So I'm talking about the core, stator core. Yeah, this is copper. Fine. This is copper. Fine. Sorry, I shouldn't mention this as the coil. This is the core, stator core. Stator core material is the same as the rotor core material. Okay. So this is iron. This is also iron. What about this gap? What is this? This is space. So this is iron. That's fine. This is air gap. So now come to the interesting part. So this is actually air gap. Okay. This is actually our air gap. So when theta m equals to 0, this is the air gap, okay, between the rotor and the stator, between the rotor circuit, rotor core and the stator core, right? So this air gap is at theta m equals to 0. Now let's look at theta m equals to 90. What is the air gap between the center of the rotor and this stator iron core? And remember, these are the iron, okay? These are the iron. So what is the distance now? Isn't it? Is it clear? What I have shown, is it clear or not?
Yes, sir.
Yes, sir.
Yes, sir.
So when theta m equals to 0, that means whenever throughout the rotation of the rotor body, the rotor d axis gets aligned with the a axis, you have a minimum air gap. You have the minimum possible air gap, isn't it? Because at any other time, this air gap is actually increasing. And at this point, at theta m equals to 90, you have the maximum air gap, isn't it?
Yes, sir.
So this is the maximum air gap, AG max, and this is the minimum air gap. So that's why we have intentionally taken these two instances of the rotor position. One is theta m equals to 0 and another one is theta m equals to 90. Theta m equals to 0 providing us minimum air gap means what? What about the permeance? In which case the permeance is higher and which case it is lower? Quickly. What happens here? Air gap is minimum. Air gap means it is one sort of resistance for establishing flux, right? If you have core here and core here, the maximum, if your path,
So,
waiting for your answer. In which case the permeance will be higher.
when
Zero.
permeance will
Sorry, the voice was broken actually. I couldn't hear. Could you repeat, please?
actually, here is a network problem from my side, perhaps.
Yeah, now it's clear. In which case the permeance is higher.
When air gap is maximum or zero.
Air gap is maximum or 0.
Sorry, air gap is minimum or zero.
Okay, air gap is minimum or 0. Yeah, when air gap is minimum, that means you are actually getting maximum amount of iron coverage between this rotor body and the stator body. So there will be maximum linkage possible. Okay. So when air gap is minimum, you have the permeance the highest, whereas in this case, air gap is maximum. So you only have this part iron and this part of iron. In between, there is a large portion of air gap. So the permeance is the lowest. Okay. This is about the highest and lowest. So when theta is 0, you have maximum permeance, some sort of maximum permeance. It gives you some flavor of maximal value. And when you have theta m equals to 90, you have some sense of minimum value. Okay. Is it okay? Now we will go forward. Now rotate this, visualize, try to visualize this to be rotated by another 90 degree. What will happen? Rotate this by another 90 degree.
The permeance will be minimum again.
Yeah, because d axis will be now here. Okay. After another 90 degree, when theta m is how much? 90, 180. So this will be 270, right?
270.
When theta m is 270, what we are getting? We are getting that your P is again maximum. You have maximum linkage. Okay, your minimum distance, minimum air gap. When it is 90, oh, sorry, not 270. After 90, sorry, you should correct me every time I'm
180.
I'm
After 180.
making this mistake. I don't know why. So this is 180, sorry. Again, I'm sorry. I don't know why I do mistake every time here. So after 90 degree from here, this is theta m 0. So this is theta m 180, right? This is 180 degree rotation. After this point, your rotor will be aligned in this direction. So it is 180. So at 180, P will be again highest. Then at another 90 degree, that is 270. At 270, what will happen? Your rotor will be along this line, D axis will be
Minimum.
along this line, right? So again, minimum. P is minimum. So that is a very interesting feature. Now, can anyone tell what will be the function, trigonometric function to represent this thing? This variation. I have explained everything. We are looking for some P expression as a function of theta, right? So we saw that at theta equals to 0, P is maximum. So let's try to draw it here.
Oh,
So it will be a cosine function.
Yeah, excellent. It will be a cosine function. So at t at 0, this is, let's say, theta. Excellent. So this is P. So at 0, it will reach maximum. At 90, it will reach minimum, and then it will move on. Now, in one cycle, how many times you are getting maximum in one cycle? By one
Right.
cycle, yeah, 2 times. So that's why it will not be a function of cosine theta, rather it will be a function of cosine twice theta. Is it clear? Because we can see at theta equals to 0, it is reaching peak. At theta equals to 180, it is also reaching peak, right? So in one complete cycle, it actually reaches the peak twice. The cycle is completed twice, from minimum to maximum. So this is the complete cycle. Okay. So as a function of theta, it is a cosine, that's okay, because at 0, it is getting to its peak. At 90, it is coming to its minimum. At 180, it is again going to its peak, right? At 360, it's completing its one cycle. So it is basically twice of the angle, twice of the theta. Now, what about the minimum value? Is it 0? Is the permeance exactly 0? I mean, should it be 0?
no, sir.
No, there is some coverage. There is some coverage of iron. Let's look at it carefully. Even at theta equals to 90 degree, there is some coverage. There is some linkage. Okay. There is some permeance available. Okay. But it is less. Of course, it is less than theta equals to 0, but there is some coverage. There is some iron here. There is some iron here. So there is some permeance. There is some permeability present because of this presence of this iron core, albeit at a very low value. So this value will not be a 0 value. Okay. Rather, it is a positive value. So at 90 degree, it will reach a minimum, but that is neither negative nor 0. That is still some positive value. So that's why, and that is its peak. This is its peak. And it will have some average value. So this dotted line gives you some positive average value of permeance, because the minimum never reaches 0. And this is the peak beyond the average. Okay, beyond the average, this is the peak value. And this is how much? This is 180. This is 270. And this is your complete 360. Okay, this is the completion of the cycle. So again, why it is twice of theta? Because this variation of the peaking of this permeance is happening at double frequency of the theta variation. Okay, so theta completes one cycle, but P completes 2 cycles. Okay, so when theta completes one complete cycle, starting from here, okay, starting from here in this position, it comes back to its first position, initial position. In that rotation, in that complete one rotation, P actually, the permeance actually completes 2 cycles as shown over here. That's why it is twice the function of theta. Okay. And it is actually drawn over here. Whatever we have discussed, it is expressed here. P equals to P average plus P peak cosine of theta m. This is the final expression of the permeance as a function of rotor position theta m. And this is your diagram or the plot P versus theta m. Okay. Any question up to now?
No.
No question. Okay, then we will stop here today. Actually, the next part covers we need to continue the next few slides. So probably we will not get enough time today for doing that. And this is the starting of some calculation steps. Okay. Remember, we are looking for the inductance calculation. Okay. Inductance calculation will allow us. Why we are looking for inductance calculation? Let me finish the lecture with this, because we targeted to calculate this lambda A, lambda B, lambda C, right? And lambda FD, lambda 1D, lambda 1Q. Why? Because we wanted to put them here and find out the expression of VFD. Now we saw that lambda A, lambda B, lambda C, they are functions of some different sorts of L values or inductance values. So now we are interested in the L's, so that when we plug in the L values here, we can get lambda and we can plug them back into this expression of voltages, and then we are done with our job. Okay. So that's why we say now that we need to calculate the inductance values. Next, inshallah, we will cover it. We'll start it, inshallah, on Friday. Okay. So if you don't have any question, then thank you very much. And hope to see you, inshallah, on Friday. Yeah. Assalamu alaikum.
Thank you, sir.
Walaikum
Assalamu alaikum.
salam.
Walaikum assalam.